we got closer to our discussion of Fourier series. We have been spending so much time on the Fourier series and especially things on the, especially the topics, okay, these things on the convergence, right? Pointwise convergence, the different boundary conditions and different types of convergence. And then, to be frankly speaking, a large part of the material actually really belongs to the real analysis. So again, why are we caring about the Fourier series so much? Where did we start from this course, which was called the partial differential equation? If you still remember that, okay? We have been spending more than I think probably more than equals to or more than 3 weeks on Fourier series. Why do we really want to do that? Okay. Now, finally, I am now using the Fourier series, okay, to represent what we have been deriving, what we have derived, okay, from our classical methods for the wave equation, okay, to show you that, okay, so first of all, the Fourier series, the solution of the Fourier series in many of the situations are completely equivalent to the solutions of the classical methods. And second, the Fourier series will be very helpful, especially when we are looking into very complicated boundary conditions, such that it's not that easy for us to obtain an analytical formula for the solution. Okay. So again, let's come back to our wave equation. Okay. Let's come back to our wave equation, which means that I'm talking about UTT equals to C squared UXX. Okay. Okay. So again, this is after such a long time, we again write a PDE on the lecture note, right? Okay. So again, can you please tell me what, according to our classical method, what was the solution to this wave equation? Let's say on the whole real line. What is the solution to that on the whole real line? What is the solution to that on the whole real line?
1/2 phi x minus
uxt equals to
1/2 phi x plus
okay.
ct
plus ct
plus
and then
plus phi x minus ct plus 1/2 c integral from x minus ct to x plus c
okay.
c y dy.
Okay. This is what we know for the wave equation. Right. This is what we know for the wave equation. Okay. And according to our previous discussion, by using the Fourier series to solve the wave equation. Okay. By using the Fourier series to solve the wave equation. What is, let's say we're considering the wave equation on the we're considering the wave equation. Okay, wave equation with Dirichlet. Okay. Dirichlet boundary conditions. Okay, between 0 and L. On 0 and L. What is the corresponding Fourier series? What is the corresponding Fourier series? What is the corresponding Fourier series for Dirichlet boundary condition on 0 and L? Well, so my uxt equals to actually n going from 1 to infinity. Okay, an cosine m pi ct over L, and then plus bn sine m pi ct over L, and then sine m pi x over L. Okay, the reason that we are only using sine series is that exactly comes from the fact that it has a Dirichlet boundary condition, so sine series. That is okay. 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 And what are exactly the AN? Because you see here, the cosine m by ct over L, sine m by ct over L, these are exactly the characteristics, the eigenfunctions for time, right? So according to the initial condition, according to our initial condition, what is the relation between phi x, between phi x, psi x, and the sum of an sine m pi x over L, and the sum of from 1 to n to infinity bn sine m pi x over L? What is that? What is that? What's the relation between phi x and an sine x sine m pi x over L? Psi x, bn sine m pi x over L. Actually, they equal to each other, right? This actually, let's recall. You see, what was our rationale coming into the Fourier series? That is exactly because we wanted to legally use the sine series or cosine series or any other Fourier series to represent the initial conditions. Right? We actually came from that. We came from that. So here, phi x equals to the sine series, the an sine series. Psi x equals to bn sine series. Of course, now we exactly know that the corresponding coefficients an and bn are exactly the Fourier coefficients and can be computed by the corresponding inner product method. So it's a bit okay. But you see, now if I'm putting this back to the Webb equation, you may yell at the beginning, right? Because you see, this solution is the solution to the wave equation on the whole real line, right? On the whole real line. Here, this is what this is only the wave equation to what? This is only the wave equation such which should satisfy the Ricci-Fourier condition, right? Okay, I accept that. I accept that what you were saying is valid, is very valid. But okay, there is still chance for us to legalize everything. Just consider that okay, we are having a Ricci boundary condition between 0 and L. And let's just simply expand everything to the whole real line. We have been doing that. Starting from one finite interval and then expanding everything to the whole real line. Okay? Then everything is still okay. Right? Everything is still okay. So that's good? Because this expression, these two Fourier series, they work between 0 and L. But with appropriate reflection and symmetrization, they also work from negative infinity to positive infinity. It's just that I need to do a symmetrization, okay? I just need to, because this is the sine series, I just simply need to do an odd function extension. Right? I just need to do an odd function extension. Okay, to first obtain a sine series between negative L and then L. And then now this becomes periodic. Then I just have to expand everything to the whole real line. Okay? This is another thing I would stress. Okay, so this can be the solution over here. Okay, it can be extended to the whole real line. Because the solution can be extended to the whole real line, then here the phi x and psi x, okay, they can be regarded as something that has a definition on the whole real line. Okay, they have the definition on the whole real line. Okay, if I now, oops, sorry, my tablet is actually running out anytime. Let's hope I can finish this part of discussion before it dies out. Okay. So okay. So now my uxt, okay, by substituting everything, the initial condition, the Fourier spaces, okay, back to the original solution, what we are obtaining over here is actually 1/2, okay, sum m from 1 to infinity, an, okay, and then sine m pi x plus ct. Don't forget that was what? That was phi x plus ct, right? Okay, so m pi x plus ct over L, and then plus sine m pi x minus ct over L. Okay, and then plus 1/2c sum m from 1 to infinity. Okay, x minus ct, x plus ct, and then bn m pi c over L, and then sine m pi s over L. Okay, ds. Oh well, okay, actually dy. dy would be better. dy. Oh, so
Why
yes. Yes. So much good? This is okay? So much good? Well, these two things, sine n pi x plus ct, sine n pi x minus ct. Okay, of course, the bracket can be opened, right? The bracket can be opened. Sine n pi x plus ct over L, that actually equals to what? That actually should equal to something like sine, cosine. So that should be sine m pi x, sine m pi ct. Okay, and then sine m pi x, cosine m pi ct, and then plus cosine m pi x, and then sine m pi ct. Right. So just to write one more step, this guy is sine m pi x over L, and then cosine m pi ct over L, plus cosine m pi x over L, and then sine m pi ct over L. Okay, this thing the same, but we will be able to cancel one term, right? We'll be able to cancel one term. Therefore, the first term now becomes, okay, and here's a 1/2. Here's a 1/2. So the two pieces of sine, cosine, okay, is going to cancel with the 1/2. So the first term now becomes m from 1 to infinity, okay, an sine m pi x over L cosine m pi ct over L. So that's good. And the second term, because I worry too much that my tablet is going to running out, so I'm going to review the answer. It's going to be, and that's actually not so hard if you want to directly do the integration, right? So that's going to be bn sine m pi x over L, and then sine m pi ct over L. See? So again, this is exactly the solution. Okay, this is exactly the solution to the Fourier to the Fourier spaces. Because here, an, bn, right? An cosine m pi ct sine m pi x, bn sine m pi ct and sine m pi x. Here, again, an sine m pi x cosine m pi ct, bn sine m pi x over L, sine m pi ct. Here, the sine m pi x, sine m pi x, this is actually a common factor, okay, for the nth term. Right. So what does that mean? What does it mean? This part, let's look at two of these things. Okay. This part is the solution using what? Using eigenfunctions. Okay. This is the solution by using the eigenfunction. This is what? This is the solution. This is the solution. Okay, coming from classical, okay, coming from classical solutions, okay, and with the initial conditions expressed in their Fourier series, right? So this, again, don't forget, this solution, it actually comes from the classical solution. It's just that I have been representing the initial conditions by the Fourier series. And you see, these two things are exactly the same as each other. Okay, these two things are exactly the same as each other. So this is the last point I want to stress for the Fourier series. You see, the whole point. Okay, the biggest point for the Fourier series when we are trying to use it to solve PDE is that sometimes it's easy for us to obtain an analytical formula. Okay, it's easy for us to obtain an analytical formula for the solution. In these cases, the Fourier series should exactly the same. Okay, should produce exactly the same as the classical solution does. In some of the cases, it's actually not that easy to obtain an analytical formula of the solutions. And in these cases, okay, the Fourier series is going to be very, very useful. Okay, at least providing us something, okay, for providing us something for evaluations and analysis, okay, of the solutions. So that's everything about the Fourier series. This is everything about Fourier series. And so that essentially closed up 5.5, and my tablet is actually running out in any time. So I've been thinking about how much that I should do for. Do you folks think you still have place in your vacancy in your brain for something for chapter 6? Okay, just a little bit. Okay, I'm going to just say a little bit. I'm not going to write it down on the tablet which means that we will be starting. I mean, even in the next class, we will be starting from the very beginning. Okay, chapter 6. So for chapter 6, where should I write it? Why don't I just simply attach and then let my tablet die in peace. And I'm going to write something, okay, on the whiteboard, on the blackboard, okay, and for the very first time, okay, in the semester. Okay. So in chapter 6, okay, we will be focusing on a very specific type of a partial differential equation, which actually does not involve the time. It's only about space. It doesn't involve the time. Because you see, previously we have been looking into the largest two types of PDEs that we have been looking into was the wave equation, right? Was the wave equation and the diffusion equations. Wave equation and diffusion equation. In the 2D scenario, in the 1D scenario, I'm having wave equation UT equals to c squared on u-axis, right? And for the diffusion equation, I'm having ut, which equals to we're using d, right? Okay, u-axis. So good. And this is again in the 1D scenario. This is a 1D scenario. For 2D or 3D scenario, the corresponding wave equation, diffusion equation will be changed to UT equals to c squared Laplace u-axis, okay? And ut equals to d Laplace u-axis. Oh, sorry, no u-axis anymore. Laplace u. We have to write this at the very beginning. And the reason that this is going to be made much more complicated, is not just that the dimensionality of the solution increases. Because if it's just only the increasing of the dimensionality, actually everything can be still. I mean, well, why don't we just simply replicate for every dimension, as what we have been doing in one dimension, and then just repeat everything. Okay. The reason that this is going to be more complicated is that the boundary corresponding the boundary. You see, for one dimension, the boundary, most of the things, in most of the cases, we just need to worry about 2 points, right? We just need to worry about the 2 points. For example, the 0 and L, okay? And there will be like a Dirichlet or Newman boundary condition, but whatever it is, we at most need to worry about 2 points. Sometimes we only need to worry about 1 point. But just consider a 2D, okay, just consider a 2D space. Then the boundary can be this. Just by increasing the dimensionality of the space by 1, the boundary now it can become much more complicated. Okay, the boundary becomes much more complicated. Because I can, let's say, for example, let's say I'm studying the wave of water, okay, in a dump, okay, in a dump, and the dump. Nobody says that the shape of the dump is a perfect circle or is a perfect square. Nobody says that. You can literally be anything, right? You can literally be anything. So correspondingly, it's actually very necessary for us to move our views, or to actually expand our views from 1 dimension to 2 or 3 dimensions, because these will be the mostly used models, real-world models, okay, for us to investigate in the future. Well, actually not in the future, but in this class. Okay, and for these type of equations, before we look into the temporal dynamics, okay, for the corresponding wave equation and diffusion equation, actually a very useful beginning, a very useful starting point for us is that what about we look into the steady state? See, what if we look into the steady state, okay, for the wave equation and the diffusion equation? For example, for the diffusion, we have already known that, okay, so let's say for 1D diffusion within a certain interval, okay? We would imagine that, okay, that actually depends on the boundary, right? But if we are having let's say a Newman boundary condition, which means that all the mass is strictly constrained, okay, within the original interval and it's not leaking to anywhere, then we would imagine that finally, okay, everything is going to plateau. Okay, we're going to have a constant function as our final answer. So the steady state, but again, that's only for 1 dimension. That's only for 1 dimension. You see, when we are talking about a steady state, it actually is about functions like uxx. So okay, again, for the steady state of a wave equation, or for the steady state of a diffusion equation, that means that the u, okay, uxt, now it becomes a relative of t. Right? The steady state means that it's not changing anymore on time. Right? Steady state means that it's not changing anymore on time. Which means that it's essentially only a function of, let me not use g, let me not use f, but let's say we are using a w. Okay. That becomes a function that's only about x. Now it becomes a function that's only about x. If a function is only about x, then its temporal derivative becomes what?
0.
It becomes 0. 0, 0. Right? So essentially, we are having uxx equals to 0 for 1 equals. And Laplace u equals to 0 for 2D or 3Ds. For 1D, what are the possible solutions for uxx equals to 0? What are the possible solutions for uxx equals to 0? Constant, of course, u is a constant. That leads to that, is 0. Uxx equals to 0. But what else?
Degree 1 polynomial.
Okay, sorry?
Degree 1 polynomial.
Which has linear functions, right? So my uxx equals to 0 in 1D case, that simply means that my ux equals to ax plus b. Well, when did we see the linear function in this class? When did we see the linear functions as a solution in this class? Actually, for the heat equation, for the diffusion equation, such that I am having one side, okay, in a thermal mass, and another side to become leaking, something like this. So, or one side in a thermal mass is to let's say to 100 degree, and another side in a thermal mass for 0 degree. is something, then we are going to see that the distribution of the heat is actually going to look like a linear equation. Okay, sorry, a linear function. So this is the solution to ux equals to 0 in 1D. But what you're going to see is that the solution to Laplace u equals to 0 in 2D and 3D will actually become much more non-trivial. It will become much more non-trivial. And these functions, okay, the solutions for ux equals to 0, okay, these functions will exactly work as what? It will exactly work as the component of the source function. Okay, the component of the source function if you want to get into the diffusion equation and wave equation in 3D, 2D, and 3D. Okay, so that's why Laplace u equals to 0. This is called the Laplace equation. Laplace. This is the Laplace equation. Well, you can memorize it because this symbol is Laplace. Laplace u equals to 0 in a 2D or 3D space. That is called the Laplace equation. And the corresponding solution u is going to be called as harmonic function. Okay, harmonic function. Harmonic function. Actually, there has been people in the history have spent a lot of time studying the properties and the possible choices for the harmonic function. And you see, this is the case when everything is homogeneous, right? For a homogeneous function. But if inhomogeneous, I'm going to have a wave equation to be something like right-hand side equals to fx, right? fxt. Let's just say fx. Right? Diffusion equation the same. Okay, fx. So that's good. Okay, this is the inhomogeneous case. Here in the wave equation, this f means that on every single point of the string, I'm actually imposing some force on every single point of the string. Here, diffusion equation fx means that I'm actually injecting mass, or I'm actually injecting temperature in the speed of fx on every single point. So that's good. Okay. Then correspondingly, the corresponding steady state now is going to change. Okay, now it's going to change to something like, okay, here, to something like uxx equals to negative fx here, or negative f here, x, y, z. Okay, so the inhomogeneous version of the Laplace equation is called the Poisson equation. Okay, the Poisson equation. Okay, so Laplace equation and Poisson equation, which represents the possible steady states for the wave equation and diffusion equation in the higher dimensional scenarios, okay, is going to be our study object for chapter 6. Okay, it's going to be our study object for chapter 6. As I said, okay, for when the dimensionality is 1, okay, the possible harmonic function is actually very trivial because that can only be linear functions. But when we are getting into 2D and 3D, okay, the possibility of the harmonic function is actually going to be very, very much, very large. Okay, and so in section 6.1, we'll be looking into okay, the basic problems of the Laplace equation and Poisson equations for the Laplace equation and Poisson equations and their solutions, harmonic functions. But okay, when we are getting into 6.2 and 6.3, okay, we will be instantly turning back to the Fourier series. Then you are going to see that all the efforts that we have spent in chapter 5 on the Fourier series now will pay off. Okay, because if we don't have the basic, if we don't have the basis, okay, of the Fourier series, then it won't be so straightforward for us, okay, to apply these methods, okay, to solve the Laplace equation and Poisson equation, especially when the boundary, is not so well defined. When the boundary is not so well defined. So this is everything that I see. And I actually will be very busy. I do apologize for inconvenience, but I'm going to be very busy today after the class. So I kindly ask you folks to, for example, come to me, let's say after 5 p.m. I will be open for questions between 5 and 5:10, 5 to 10. Sorry, 10 after, from 5 to 5:10. Okay, I'll be available for questions, but not before nor after that. Sorry, I'm very sorry about that because my schedule is exploding. Okay, for today. Yes. Okay, but I will be much more available on Wednesday and Friday. So if you have any questions about today's lecture or any other questions, please come to me on 5, and I'm going to stay there in my office for 10 minutes. Okay. Thank you, everyone.